started with the second session now on types. Topic near and dear to my heart. So first up, we have Philipp presenting about abstracting control.
Yes. Hello, everyone. I'm Philipp. The title is Typing, Representing, and Abstracting Control. Notice the Oxford comma. This is joint work with my colleague, Jonathan Krafthäuser. So let's say our goal is to implement a language with control effects. This means the programmer has access to control operators like, for example, shift. This is an old goal, and it has lots of well-known and old solutions. One of the solutions is conversion to continuation passing style. Because this goal has so many old solutions, our paper is heavily based on three other papers. The first one is Subtyping Delimited Continuations by Matersok and Bernatsky. The second one is Representing Control by Dombey and Filinsky. And the third one is Abstracting Control by Dombey and Filinsky. But this is a functional curve. So we took these parts and we chopped a few things off perhaps, and then we rearranged them to make all of these three things fit perfectly together. What helped immensely in doing so was that we are using types. We're embedding our source language and our target language into dependently typed language features. For example, we index the types of our statements by a list of control effects. After this introduction, let's go to some examples to give you a feeling for the kinds of programs we will want to write. Let's start with our first effectful function, fail. Fail uses shift 0 to capture the current continuation, but it never resumes the continuation. Instead, it immediately aborts with string no. The type of fail says that it is an effectful statement, and statements are indexed by a list of answer types. In this case, the topmost, the fourth answer type has to be string because we expect in shift 0 that the context is able to receive a string. Please ignore the colors for now; they will make sense later. Our second example is flip. Flip captures the continuation and resumes it twice, once with true and once with false. Statements are not only indexed by a list of answer types, but also by an immediate results type. The immediate results type here is bool because we resume the continuation with true and false, respectively. Do notation sequences effectful statements. We don't look at the results, we just run the continuation for its side effects. Our third example will be emit. Emit takes a value of type A and emits it to the outer context. It captures the continuation once again and resumes the continuation with unit to get a list of future results. It then prepends the given A to this list. Because it expects the continuation to return a list of A's, and also because the body of shift itself returns a list of A's, the first answer type has to be a list of A. Okay. We can compose these effectful smaller functions into larger effectful functions. Image triples here. What's important is it uses this triple function that in turn uses fail and flip to generate triples. And so the first answer type has to be string. It also uses emit on the second level to emit the triple to the outer context. Because we did have two control effects here, when actually running this image triples, we are delimiting both control effects with reset 0. Because we've delimited two control effects, we end up with an empty list of control effects, which is to say emitted triples is pure. It does not have any control effects, it's just a list of triples of integer. Okay, after after I've shown you these example source programs, I want to show you the kind of code we're generating for this. It looks like this. What's important here is that internally it uses continuation passing style on two levels, these K1 and K2 arguments. What's also important here is that there are no unnecessary beta redexes generated by our transformation to continuation passing style. This is the code you would write by hand. Except, well, yeah, right, you don't want it. Okay, after this whirlwind tour of the kinds of programs we want to compile, let's slow down a little and review the basics of continuation passing style. This is the type of expressions in continuation passing style. It has answer type R and immediate result A. I will call expressions with this type effectful expressions. We can define our first control operator, shift 0. Shift 0 takes a body, and the body in turn takes a continuation from A to R and produces an R. Shift 0, as opposed to shift, removes, does not instantiate a delimiter in the body. So the types tell us that the continuation is pure, and the body of shift 0 has to appear true, because any control effects that the body would have could be unlimited. The implementation of shift 0 is pretty easy, it's identity. Shift 0 also has an inverse that we will call run 0. It's similar to Kiselius and Chant's dollar operator. Given an effectful expression and a context, it will run the effectful expression in that context. I've already hinted at the implementation of run 0 because it's also identity. With this run 0, we can define a more traditional reset 0 that delimits all control effects in an effectful expression. It runs the effectful expression in the empty context. The empty context is identity here. Note that the answer type and the immediate result type have to agree. We want to compose effectful expressions into larger programs. For this, we will define monadic combinators. The first one is pure. Pure takes a pure expression and makes it into an effectful expression. It calls the current continuation with a value. To define bind, we will first define a helper function called push. Push takes an effectful function and a stack and pushes the effectful function onto the stack. What this means is that once the result stack is called with an A, we will run the effectful function with the A and with the stack A. Given push, bind is easy. Given an effectful expression and an effectful function, we run the effectful expression, but only after pushing the effectful function onto the current stack. This is just the continuation monad, and pure and bind will allow us to use do notation to write larger programs. Okay, after reviewing these basics, we want to actually generate programs in our target language. For this, I'll first explain how we represent our target language. This is a typed higher order abstract syntax, and to be more suggestive, we will write it like this, where the expression type constructor will be written in orange with an underscore, and expressions in the target language will also be written in orange with an underscore. To generate code, we want to generate code, but we don't want to generate all of these abstractions and applications that you've seen previously or that you're seeing here, because that would mean a lot of plumbing of continuation arguments at runtime. So what we're doing is we are changing our type of continuation passing style to work on expressions in the target language, but be in the meta language. That's daily. These orange underscore things are expressions in the target language, and we've chosen to name our type of continuation passing style now blue with an overbar to suggest that it's at the meta level. This is just a specialization of the type. On the term level, nothing changes. Okay? Similarly, for our monadic combinators, we changed them to work with our new type of continuation passing style, and on the term level, nothing has to change. To then actually, in the end, generate code in the target language, we define reify that takes such an effectful expression on the meta level and reifies it into the target language. And also, it's another operation reflect that reflects effectful expression in the target language back into the meta language. Reify creates an abstraction and then runs the given effectful computation with a function that, when called, will generate an application of the continuation to the argument. The two are nicely symmetric. Okay, I've shown you the basics, and then I've specialized the type of CPS to allow for generation of code in the target language. Now I'll go back to the basics and specialize it in a different way to allow multiple levels of control. Remember, this was our type of expression in continuation passing style. but we can iterate it to get the CPS hierarchy. What this concretely means is that the answer type is not pure, but is again an effectful expression. And then in turn we can iterate it again to make the answer type again be an effectful expression. We define an abbreviation that we call statement that takes a list of answer type and then iterates the CPS type constructor on this list. A statement with an empty list of answer types is a pure expression. This was the definition of our basic control operators that we had before. And now we upgrade it to work on statements. Again, this is just a specialization of the types. The terms stay just the same. Well, it's not entirely true. In Recursive 0, the empty context is not the identity function anymore, it's pure, the pure function. Similarly, for our monadic combinators, we extend them, specialize the types to work on statements with a list of answer types. And again, on the term level, nothing has changed. But we had to add special cases for when the list of answer types is empty. For when we already have a pure expression, for example, we don't have to do that. To go up in the CPS hierarchy, we will define a new combinator lift that lifts a statement with a list of answer types into a larger context, so we can use it with one more in a context that has one more answer type. Lift is just bind, and the types and implementation just works out. With lift, we can define a hierarchy, define a hierarchy of control operators, for example, shift 0, 0, shift 0, 1, shift 0, and so on, by lifting an appropriate number of times the basic control operator shift 0. Now, I've extended the basics, I've specialized them to be able to generate programs in the target language, and I've extended them to allow for multiple levels of control. The question is, can we do both? And the answer is yes. This is what we had, where we had control operators on multiple levels of control, and we can do the same thing we did previously by having them work on expressions in the target language. The same works for the monadic combinators. Instead of having it all on the meta language, we can have them work on expressions in the target language. Now, in the end, we need to reify our effectful statements, and for this, we have mutually recursive functions, reify and reflect. Reify, for example, if we don't have any control effects, will do nothing. And reify, if we do have control effects, will generate an abstraction for the continuation, and then recursively reify the body of the computation after reflecting the continuation. That's why the two are mutually recursive. So to sum up, we've presented a nicely fitting synthesis of subtyping delimited continuation, representing control, and abstracting control. The thing my colleague wants me to tell you is you should index your effectful functions by the list of answer types. The list of answer types corresponds to the types of delimiters from innermost to outermost. And the effect types we're using guide the CPS transformation we are doing, so that, for example, we don't generate any continuation passing style for pure expressions. In the paper, we are also showing how to avoid eta redexes, and we also show how to deal with branching and recursion. That's it. Thank you. Any questions?
We have plenty of time for questions. Yes?
Using this, is there an easy way to reason the interaction between effects?
The question was if there's using this an easy way to reason about the interaction between effects. I think no, not directly, but you could add something, I guess. Yes?
That is shift operator 0, 1, 2, 3. Parameterize them and compute out a single level parameter.
Can you repeat
yes.
the question?
The question was if these control operators shift 0, 0, 0, and so on, if they could be parameterized and then generated. And I guess yes, if you could somehow, you mean if this index was on the type level, you would have to somehow reflect it to the value level to then unroll the appropriate number of lists, I guess.
Could you do this for an arbitrary stack of monads rather than just CPS monad?
The question was if we could do this for an arbitrary stack of monads rather than just CPS monad. And I mean, probably you mean the staging part, or which part? Well, okay.
You have a very nice presentation of what goes on with stacking multiple CPS monads.
Yes.
Right, so it would be nice to have a similarly nice organization of what happens if you have a stack of monads with other kinds of effects.
Yes. I'm not sure how that would look like, but other monads factor through the CPS monad, so I would recommend people to use that instead. Yeah, please.
Are you using Idris's partial evaluator to spit out the regex-free code at the end?
The question was if I'm using Idris's partial evaluator to remove redexes, right? The answer is no, we're not using the partial evaluation feature of Idris. It falls out because we are careful to generate code on the meta level, and those redexes will not end up in the target program.
Actually, I have a question. So, what features of Idris do you think were sort of central to this idea? I mean, was that choice of Idris essential or incidental?
The question was if there were any features of Idris that were very essential to this development. And I think no. What we're using is a type level list, and in some cases implicit type level parameters, but I'm very sure this could be done in other languages, for example, even Haskell, with the appropriate number of extensions. Yes. Yeah.
So you had reflect and reify, which were mutually recursive. Did you have problems with getting Idris to accept those as well typed? I don't know Idris, so I don't know whether that's a useful question or not.
So the question was if we had problems getting Idris to accept these mutually recursive functions, and the answer is no. And I'm not sure if we should have, and I'm not sure why we didn't have the
So the one-way continuations I'm familiar with, they have things like named prompts, and you can capture continuation up to a prompt that satisfies a certain tag. Can you type that nicely, maybe using phenotypes would actually make it easier to express that?
The question was, there are other styles of control operators that have prompts, and the prompts are named, and then you can capture the continuation up to a certain prompt. And the question is, how does this fit in with this? So I think yes, it would be possible, and the type level list would also have to include the name of the prompt, and then the operation shift to prompt would do a type level search to generate the appropriate number of lifts. But note that this is static control. What this means is that there cannot be an unknown number of prompts generated or an unknown depth of continuations. Yeah.
Would you possibly be able to sort of name your tail of your list with a set of prompts that I know are in scope, I just don't know where they are.
The question was if we could name the tail of the list of answer types with a set instead of a list, so that we know that the answer types or prompts are somewhere, but we don't know exactly at what position. And I think, no, that wouldn't work well. We need to know the number of lists we have to insert. But we've been experimenting with, if you have a proof that, a type level proof that something is a member of a set, and you represent sets as, I don't know, lists or something, then this type level proof somehow gives you the position in your representation, and we've been trying to use that to generate the right number of lists.
Okay, great. Let's thank Philipp again.